Hello everyone, and welcome to the first part for the section 3.2 notes, where we are going to be introducing the idea of polynomial functions. And before we start to get into any of this nitty-gritty, why don't we just go ahead and define what a polynomial is. Now, if you think back to the previous section where we're talking about quadratics, I mentioned that a quadratic function is just a type of polynomial. Because of course, all that it means polynomial is it's going to be a function that it does not have to have only one variable, by the way. You can have polynomials that have many variables, but a function whose terms basically look like this, whose terms look like x raised to some power over here. And it doesn't matter what the power is, I'll just write x to the k power. And then it's possible to have a coefficient in the front. And so the terms look like this, where this one over here, this is just some number. I will just say some real number. Because it does not have to be a whole number, it does not have to be anything in particular, only a real number. And then this power over here, this does have to be a whole number. And it also has to be positive. And so we don't want any negative powers, we don't want any fractional powers like square roots or cube roots or anything like that. It's not possible. And so in this case, if you have a function that has terms that are basically added and subtracted from each other that look like this, the terms look like this, then this would be in particular a one variable polynomial. We could have a multivariable polynomial that would have some other variables. Like, why don't we see an example of a polynomial? In this case, there's something called a monomial, which is, this is just a polynomial with one term. And it's possible to have a term with multiple variables that maybe looks like this. It could have just a coefficient in the front, and then it can have x raised to some power, y raised to some power, and z raised to some power, for example. This would be a polynomial, and in particular it would be a monomial because there's only one term over here, provided that these powers, the k, m, and n, I should say, these all have to be whole numbers, positive whole numbers, and this coefficient in the front has to be a real number. If it meets these criteria, then this would be a multivariable polynomial that has only one term, so it would be called a monomial. And we see here the general form, and I don't want this to look too confusing. The general form that we have for a polynomial. A polynomial is anything that meets this definition. And that's what I was talking about before, that the terms will look like this, because it's possible to have basically as many terms as the degree of the polynomial, where here the degree of the polynomial, well, why don't we just define this term? The degree is the highest power of x that does not have a 0 as the coefficient. Because of course, if one of these coefficients, especially the one in the front, if the coefficient is 0, then that x term is times 0 and it basically disappears. So the highest power of x without a coefficient of 0. Coefficient, I'm misspelling this one, without a coefficient of 0. And so that's what we're dealing with this polynomial here, the way that it's written. We should specify that these numbers, for example, these ones an minus 1, these ones are just, let me write it here like ai. These ones are real numbers. That's what it means. AI is an element of the set of real numbers. For I that can go from, actually it starts at 0, we see that the first coefficient down here is actually a sub 0. So 0, 1, counting up to n. So there's just n of them. We don't know what n is. But here we can tell, as long as this coefficient, the a sub n, if this one is not 0, then we would say that this is an nth degree polynomial. So this one here is nth degree polynomial, provided that a sub n is not 0. Why don't I just write that? If a sub n is not equal to 0. And we're going to be talking a lot about different aspects of polynomials, especially finding the zeros of polynomials. In other words, finding the x-intercepts. The first idea that we're talking about, though, is this idea of the end behavior. The end behavior of a polynomial, where the end behavior is basically talking about what happens in the graph whenever you're on the far ends, on the left end and on the right end. And these ones are also, you could think of maybe as infinite behavior, because it's basically as x is going towards negative infinity, we're wondering what's happening to the y value, and also as x is going towards positive infinity, we're similarly wondering what's happening to the y value. And so I just want to draw a picture here of kind of what's going on with that one. We have some experience with the polynomial that just goes x squared. Here, this one is a graph for the function x squared, where y is just equal to x squared. And the end behavior, what we're interested in is what's happening on the ends. So in other words, are these arrows, are they going up to the left, down to the left, maybe up to the right or down to the right on the ends? And there's actually a common theme between all of the polynomials that have an even degree. So remember, the degree is the highest power of x. And here, this is a second degree polynomial. And anytime we have a polynomial with an even degree, the end behavior will look the same. Basically, as long as the coefficient in the front is positive, because remember, if this coefficient in the front is negative, it's going to reflect the thing across the x-axis, and it's going to be facing down instead. So why don't we think about that one as well. If we have a function like maybe negative x squared, it will be facing down. And so what we will see is that for even degrees, even degree polynomial, always the arrows will be going in the same direction. They'll either both be going up or they'll both be going down. And so we could make a fact about that. But in general, I want to say that the end behavior, or in other words, what we're going to be writing for the end behavior is this new notation with an arrow, where we will say as x approaches infinity, that's how we will pronounce this one. As x approaches infinity, that's how we would pronounce the arrow, is this approaches thing. As x approaches infinity, we will have y approaches infinity. And also whenever x approaches negative infinity, y approaches infinity. This will be the case whenever the coefficient for x squared, so this coefficient, if that coefficient, let's just call it a, for example, if that coefficient is positive, then both of the arrows will be doing the same thing. That's what I mean to be talking about here, is that these will be the same. The end behavior, either the y value will be going towards positive infinity on both sides, or else it can be going towards negative infinity if the coefficient in the front is less than 0. And so in general, even degree, what we're talking about, let me just write down the general form of an even polynomial. It will go with the coefficient a in the front, and then x will be to some even power. And by the way, you can write an even number always as 2 times something. Then we'll know for sure that it's even. So this number could be 0 up until, and actually we don't want to start at 0, we should start it at 1. As long as n is something from 1 up until basically anything that we want, you multiply it times 2, you'll get an even number, and then we will have a coefficient in the front like a. And so if that coefficient is positive, then whenever x goes towards infinity or towards negative infinity, y will be doing the same thing, going towards infinity. And then if the coefficient in the front is negative, we will have the opposite situation, that as x approaches basically positive or negative infinity, it doesn't matter, y will be going towards a negative infinity. And that's the case that we see right here. And so we will have that for the even degree polynomials, that they either will have both arrows going up or both arrows going down. Whenever we have an odd degree polynomial, and we can write a general form for odd degree polynomial, which here I'm neglecting to add any more terms, but as many terms as you add, it doesn't matter. I will make that as a little note right here. The end behavior, for sure, without a doubt, it only depends on the highest degree term. And so I would want to call it the first term, but it doesn't have to do with which order it's in. It has to do with which degree the polynomial is. So it depends on the highest power term. Why don't we call it that one? The highest power term, for sure. So if you have a polynomial that has a bunch of terms in there, you just look at the one which has the highest power of x. That term is what is going to tell us the end behavior. And that's the one that we're interested in looking. Is it even or is it odd? And so odd degree polynomial, we can neglect every term except for the highest degree term that will go, in this case, we can call it the power 2n plus 1 because this will be an odd number. If n is something from 1 just going as high as you want. We will have this type of end behavior that as x approaches infinity, and here let me draw a picture of what odd degree polynomial would look like. It doesn't matter very much about it. It will look similar to the cubic function. The same way that every even degree polynomial, it ends up looking on the ends like a parabola, like the way the quadratic function looks. It's the same thing with the odd degree polynomial. The ends, this end behavior, it will mimic what's going on with a cubic function. And so if you can at least remember what quadratic function looks like and what cubic function looks like, you can remember what is the end behavior for even and odd. We can end up having all kinds of different stuff going in between, but all we care about right now is what happens to these arrows on the very periphery of this one. So as x approaches infinity for this one, and here we're dealing with the case where a is positive. Of course, x going to infinity, it's going to the right side. Y is also approaching infinity. And then as x approaches negative infinity, which is the left side over here, we have that y is approaching negative infinity as well. And then we would have the case whenever a is negative. If you think about what that graph looks like, it's just flipped upside down version of this one. So we will have, as x approaches infinity, which now that's on the right side, y is going towards negative infinity. And whenever x is approaching negative infinity, so we're over here on the left side, we have that y is approaching positive infinity. And so we have these rules to think about for the end behavior. Now, in the next video, we will try some examples about this, and then we'll start talking about some of the other features of polynomial functions. But anyway, thank you guys for watching.